Okay, so back for more. So now we're looking at E2 eliminations of two cyclic cyclohexane alkyl halides. And the question is, which of these two occurs at a much faster rate? What we have to remember is for an E2 reaction to happen, the Cl has to be in, or the halide itself, so bromine, chlorine, iodine, has to be in an axial position. So we'll just write that up here. Axial halogen equals the reactive conformation. Axial halogen, reactive conformation. So now we have to take these structures and convert them to chair structures to figure out if they are axial or equatorial and the relative stability of our structures. So we're going to draw chair structure. These molecules or these atoms are 4 apart. So we have a CH3 axial in the 1 position. And in this 4 position, we have a Cl going up. That is an equatorial Cl. So I'll draw in the other H's here. So in this chair conformation, we do not have an axial halogen. So if it needs to react, it's going to have to flip to the other chair conformation. So in doing so, that 1 position comes down, bringing the CH3 from the axial position to the equatorial position. And this corner flips up, and the Cl was equatorial, now it's axial. So this is the non-reactive conformation, and this is the reactive conformation. Why is this one reactive? It's reactive because we have 2 different hydrogens that are both antiperiplanar to the chlorine halogen, the chlorine leaving group. So this hydrogen is antiperiplanar to that chlorine. Also, this hydrogen is antiperiplanar to that chlorine. So this is the reactive conformation. If we wanted to draw a mechanism for this, we would just do the take the base. It's using its electrons to deprotonate this position. The carbon-hydrogen bond electrons are going to make a double bond there, and the chlorine's leaving to produce the product, which is that. Since we said it could also have deprotonated that position, it's going to make that molecule and this molecule. And what you should also be thinking about is, oh, are those the same molecule? It turns out that they're enantiomers, so they are different stereoisomers. So that's that one. So we have a reactive conformation and non-reactive conformation. The question at the top, though, is which of these occurs at the faster rate, this one or the second example down here? So we have to evaluate the stability of the chair structures here, and specifically the stability of the reactive conformation chair structure. So we'll start out the same way, just drawing the chair the same way. So this is the 1, 2, 3, 4 position. The CH3 is going down. The chlorine's going up. So this is a very stable chair conformation. Also, it's a very stable chair conformation, and it's a non-reactive one, right? We said at the top, axial halogens equals reactive conformer. In this conformation, the chlorine has no hydrogen atoms that are antiperiplanar to itself. So this is a non-reactive conformation. So it has to flip to the reactive conformation. And let's first draw that conformation. So it flipped. That CH3 is now going down axially. The Cl is now coming up axially. And it now has, just like the other one did, two axial hydrogens that are both antiperiplanar to itself. But the main difference here is up top, the stability of these two conformers was about equal. This one had one axial, one equatorial, so let's write that. One axial, one equatorial. This compound had one axial, one equatorial. This conformation had one axial, one equatorial. Down here, we have two equatorial substituents, and over here we have two axial substituents. So as far as the relative stability of these, we are going to have way more of this than this one. There's probably still going to be some of this one, probably like less than 5%, and it will switch back and forth, but it's going to spend way more of its time in this conformation than this conformation. What else do we know about this conformation? This is the conformation where the chlorine is axial, so this is our reactive conformation. So comparing, and it will react, so this also is going to produce a mixture of two enantiomers when it's deprotonated by the base. So again, that will happen, and it's going to produce a mixture of this and this molecule, which again are enantiomers. So which one is going to produce that enantiomeric mixture faster? This bottom reaction or this top reaction? Well, in the bottom reaction, we're in this conformation, the non-reactive conformation, almost the entire time, whereas this top case, we have a 50-50 mixture of conformations at all times. So essentially the top molecule is in the reactive conformation more often, which makes the reaction faster. So this is going to produce a faster reaction. This is a slower reaction. Faster reaction because the reactive conformation is inhabited by that molecule for a greater period of time. So that's how you can analyze these and figure out their rates. We also, in class today, figured out that in some cases the reactive conformation is only going to lead to one of two possible constitutional isomers. So that's the other thing that you really have to think about here. And actually, that's what it says on the notes here. You must be able to answer questions relating the stereochemistry of alkyl halides to 1, the regioselectivity of alkene formation. So regioselectivity means which constitutional isomer is being formed. And 2, the rate of the E2 reaction. That's what we just talked about again up here. So that being said, thanks for working hard. I appreciate all your hard work, and keep it up. We are coming down the home stretch, and it's snowing, but I will see you guys later. Have a good weekend.